This is going to be a math talk. There will be a little genomics in it, but mainly mathematics. So I'm glad it's the start of the day where you're still awake. We'll get started here. So I'm going to talk about something called the principle. And this is a device or a principle for constructing optimization algorithms. I like to quote my former colleague at UCLA, Robert Jenrick. He said, all of classical statistics reduces to least squares and maximum likelihood, and maximum likelihood estimation reduces to iteratively weighted least squares. So we're going to be dealing with that today. And this, I'll say something about not necessarily the reduction process, but how to treat a lot of different maximum likelihood problems from this new perspective. You may have seen the EM algorithm, which is not an algorithm, it's also a principle or prescription for constructing algorithms. In bioinformatics, the most common use is admixture, normal Gaussian admixture analysis. So the algorithm or principle is a generalization of the EM, and it works by creating what we call a surrogate function, a substitute function, and that substitute function should fall above or below the objective. And when you optimize the surrogate function, you drive the original objective function in the correct direction, either uphill or downhill, depending on whether you're optimizing, maximizing, or minimizing. So stands for majorize, minimize, or minorize, maximize. So here's some history. I'm not going to go through this in any detail. You can see some of these references date back to a century ago, or almost. And what happened is people discovered specific examples of these EM and algorithms, but they didn't really understand the utility in general of what they were doing. In statistics, my colleague, Jan de Leeuw, he was the first chair of stat at UCLA, wrote a paper using for the first time in statistics for multidimensional scaling. The same year, 1977, Dempster, Laird, and Rubin wrote a paper on the EM algorithm. They named it, and that paper has, as of yesterday, 73,000 plus citations. So it's one of the most cited papers in statistics. De Leeuw's paper has 200 or 300 citations, but it's equally important in a foundational sense. One of the early theoretical papers was this one by Weisberg and Eckhart, German, and they revived work of Weisfeld and facilities locations. Here are some of the areas that have benefited from this principle. I'm not going to go through those. I used to list them A, B, C. I ran out of the letters of the alphabet. And this is really just a subset of the possible applications. I put it up there to convince you that there's something of substance here. Okay, so what's the rationale? I have 6 reasons here. One of them is you can avoid matrix inversion. And if you look at classical optimization algorithms, in statistics, many of them are Newton's method or Fisher scoring. They both involve solving often large-scale systems of linear equations. That can be expensive. Now, can help you separate the parameters of a problem and turn the surrogate function into a parameter-separated function that you can optimize one parameter at a time in parallel. So you could put these things on a multiple CPUs or GPUs. A MM can linearize an optimization problem. What that means is the surrogate is quadratic. When you look at a stationary point, you get linear equations. It can deal gracefully with equality and inequality constraints. It can restore symmetry. And finally, it can turn non-smooth problems into smooth problems. We'll see lots of these today. So the idea is rather simple. F of x is your objective function. You're trying to, in this case, we'll talk about minimization. You're trying to drive it downhill. So you create this surrogate function, g, which is anchored at a current iterate, theta n. So n is iteration number. And theta here can be a vector of parameters, not necessarily a scalar. So the surrogate function has to satisfy two conditions. One I call tangency. The two functions have to kiss at the current point. And the other is domination. The surrogate must fall above the objective. And the nice thing about this notion of surrogate function, you can work piecemeal on a complicated function. So a complicated function may have simple parts which you want to leave untouched, and then you can work on the hard parts and minorize or majorize as you need those parts. And we'll see that how that works later. So if you're maximizing instead of minimizing, you turn this around and you still have the tangency condition, but the domination condition, the inequality gets reversed. So your surrogate function falls below the objective when you're maximizing. Okay. And if you take the surrogate function and you optimize it on its left variable, you already know theta n, you don't know the theta n plus 1. When you optimize the surrogate, you get your next iterate. Okay, so I'm going to show you this, a little cartoon of how this works, so you can fix in your mind the geometry of this. And it's quite simple. You're at a certain point on that curve. This is a one-dimensional example. You create a surrogate. There's the surrogate. It's tangent to the objective. And what do? You minimize the surrogate. Now, when you do that, you take the objective downhill. You put a new, you project, you look at where the red curve projects on the horizontal axis, you project back up to the curve, you get the second yellow or orange point. You create a new surrogate. See its tangent, it falls above. You optimize it. That gives you a new point on the surrogate curve and a new point on the objective curve. And you just keep doing this until you hit the bottom. Okay, that's the whole thing in a nutshell. Let's see if we can do that again, just so you get this tangency. That's minimize, majorize, minimize, majorize, minimize, so forth. Okay. So what drives this process is this sequence of inequalities. So if we go from right to left, the far equality is just tangency on this line here. The next one is you're minimizing the surrogate. That gives you the first inequality going from right to left. Now what this means is you don't actually have to minimize the surrogate. You still get this if you drive the surrogate downhill. And then the last inequality is majorization. And if you look at this whole thing, you see that you've driven F downhill. So the idea is you're making progress minimizing the function you want to minimize. And this tends to make the algorithm quite stable because you're always making progress. It may be very slow progress, but you're always making progress. And as I note here, you don't always have to minimize the surrogate. You can often just reduce it. Okay, so there's a difference between the geometric picture and what you have to do in practice. In practice, if you want to create a new algorithm, you have to deal with inequalities, and you need some skill in doing that. And a lot of these are based on convexity and concavity. So if you want to be good at this game, you have to go back and brush up and learn stuff about inequalities. So the EM algorithm depends on something called the information inequality, and it's a probabilistic notion around the idea of missing data in an abstract sense. For convex functions, convex objectives, you have the chord above the graph property. That's used often in image reconstruction. You have also the supporting hyperplane property. I'll illustrate these in a moment. This quadratic upper bound principle will illustrate in a very simple example. And then I list a couple of other classical inequalities that have turned out to be useful in this context. So you can see there's literally thousands of inequalities, and but a few of them are much more basic than others. And these are the ones that most often turn out to be useful. So the curve here is convex. The supporting hyperplane inequality is the line beneath the curve. The chord above the graph is, that's basically what's called Jensen's inequality. Okay, so the supporting hyperplane, you can see it already. You have a nice tangency.
I have a question.
Yes.
How do we guarantee that we can find a hyperplane that is attaching to the problem space?
Well,
Isn't there some gap if we are not understanding the space very well?
okay, so every convex function at every point basically has a supporting hyperplane.
Then we are assuming the problem is about...
If you don't have a convex function, it may not work.
Then we have to design the domain in order to have that property, right?
Yeah, you have to be clever here to get this sometimes to work. But you may have a piece of a complicated function that's nice and convex, so you can deal with that with this trick. Okay, here's this first and simplest example. Minimizing the cosine of x. So the first thing you do is you take a second order Taylor expansion. So that's that top equation, and on the far right you see an intermediate point z between your current iterate xn and your potential new iterate x. And because the cosine in absolute value is always less than 1, this function is actually falls above the cosine curve. And you can see if I set x equal to xn, I simply recover the cosine of xn, that's tangency. So it satisfies both tangency and domination. Now this function is a quadratic in x. We can take its derivative and set the derivative equal to 0 to get the minimum. And that gives us our next point. So what have we done? We've created a quadratic surrogate. We turned it into a linear problem by looking for a stationary point. We solve that, and we get our next iterate. And this is a graph of what you're doing. You can see as you descend into that deep valley of the cosine function, the surrogates become better and better. They hug the objective function very tightly, and that gives you fast convergence. If you have a surrogate that is only loosely approximating the objective, you will get a slow algorithm. And here is MM compared to Newton. They actually both converge very quickly. Newton can unfortunately head in the wrong direction, and you can head towards a maximum instead of a minimum. MM is reliably going downhill. And here, oddly enough, they both converge at a cubic rate, which is extraordinarily fast, and MM actually beats Newton's method. This is contrary to what actually happens in practice. Newton's method is quadratic rate of convergence, typically very quick. MM is almost always linear or worse. So it's linear can be good, but it can also be very slow. Was there a question? No. Okay. Okay, here's another problem. How do you calculate a sample median? Well, you can do it by sorting, or you can do it by purely calculus. The calculus approach says, take that top equation, f of theta, and you're looking at the absolute deviations from your sample points, the yi. And if you minimize that function, you get the median. Now, I'm not going to prove that fact, but it's an interesting fact. And here, you can set up quadratic. You can work piece by piece. For each I, you have an absolute value that you majorize. And here's the surrogate function for one term in that sum. You'll notice that it's quadratic. And the reason that it is majorizing this p, the left-hand side, is this absolute value. If you rearrange this inequality, you get an inequality which is obvious. And that inequality is actually, both sides are actually 0 when theta equals theta n. Okay? So you have a nice majorization. You have the tangency condition. And because you can work piecemeal, you have the overall majorization. So the original function looks something like that. It has these points of non-differentiability when you cross a data point. The quadratic is smooth. You can go to the bottom of the quadratic and improve your estimate of that least absolute deviation problem. So there's the surrogate. When you differentiate that g function, the surrogate, and solve for theta, you get a weighted average of your points, your original data points, and the weights are these reciprocal absolute deviations. Now, it could be that a weight is equal to infinity when this yi minus theta n is 0. In practice, that doesn't occur, but there are ways of constructing at least approximate algorithms that solve a very good approximation of this problem, which don't have that problem of infinite weights. By the way, this also works for finding quantiles as well, but you have to change the loss function. But you can view those problems as optimization problems. Any questions about those examples? The next one I want to show you is how you find a root of a polynomial. Now, this is predicated on the polynomial having only real roots. They may have multiplicities greater than 1. Certainly, if you take a characteristic function of a symmetric matrix, you know that the roots have to be real. So this is a problem of some interest. I've written the factorization of the polynomial in terms of the roots. That's standard high school stuff. If you take logarithms, then you reduce to a nice quantity. And if you remember from calculus, you can take the log, you can take the derivative of the log of an absolute, and it's 1 over x minus rj. Now that's assuming x does not equal rj. Okay. Okay. That's what, and of course that's the same as saying p of x does not equal 0. Now if you take now the derivative of your log of the absolute value of the polynomial, you get this guy. If you take another derivative, what happens? You're going to bring out a minus sign, you square your reciprocals, and now you get a negative value for that second derivative of the log of the absolute value of p of x. Okay, so this function is concave between its roots. Unfortunately, it will go to infinity if you're right at a, or minus infinity if you're right at a root. Okay, so here's a simple example. I'm plotting the log of the absolute value of p of x. It has 2 roots. You can see that between roots, or beyond all the roots on the left or right, you have a nice concave function. And you can put a tangent line to any convex function, a concave function that falls above the function. Unfortunately, if you want to use a linear surrogate, that linear surrogate has no minimum. So we have to deal with that. Okay, so the top is the linear majorization. We're trying to drive the objective down to minus infinity, basically. So what we do to stabilize matters is we introduce another term, this c over 2 times x minus xn squared. Now that surrogate function is no longer linear, it's quadratic, and it has a nice minimum. And we can find the minimum, differentiate with respect to x here, and here's our update. And that is if you think about it, the case C equals 1 is just Newton's method for finding the roots, a root of that polynomial. Okay. So if you go back to the graph, unfortunately what happens, so your new surrogate is now the green curve. It has curvature, it's a quadratic. You can find its minimum. Now its minimum may take you outside one of these regions between two roots. So to make this work, sometimes you have to back up. It's this process called step halving. Take half the step length or a quarter of the step length or an eighth. So you get back and you actually experience a decline in your objective. Now it doesn't mean you can't cross one of these boundaries, but through step halving you will actually force the Newton's method to decrease the function in question. Okay. And here's some examples. Now, Newton's method, this polynomial has two roots. One of them is repeated. You get rather slower convergence for the repeated root. You get faster convergence for the root of multiplicity 1. And it works, and most of the time you're not step halving. You can cross those boundaries between roots, but this seems fairly reliable. Okay, let's go back to statistics. If you've taken a statistics course, when they talk about maximum likelihood, they always give you these examples where you can find the estimates, the maximum likelihood estimate. This is an example where there's no closed form solution. So it's the Cauchy distribution with a location parameter mu and a scale sigma. Now, if you take a sample, you're going to have m sample points. You're going to take logs of that crazy function. When you differentiate and try to solve, you're going to get, basically, after you simplify, ugly polynomials of high degree, which there's no obvious solution. But you can, so when you take logarithms of f of x, think of replacing the residual, standardized residual x minus mu over sigma, that's squared by y, you're going to get functions that look like that. Minus log of 1 plus y. Now that's a convex function. Yes. So you have a supporting hyperplane minorization. And that's what's going on here. This gives you the minorization. And this is basically involves a derivative of this function h. So you take the minorization in terms of y, and then you replace the y's by the standardized residuals. Now, this is nice because this is exactly the form on the right that you see when you're estimating the mean invariance of a Gaussian distribution. It's weighted least squares. So the solution, the location, is a convex combination of the sample points, and the variance you can solve for the variance is the square of that square root. So it's something that's fairly obvious. So these updates do a very nice job of driving the log likelihood uphill. And if you want a good starting point for mu, you would just take the sample median. And if you take the sample in interquartile range, that's actually a reasonable starting point for sigma. And these things are not that hard to code. This is my Julia code for solving this problem. By the way, if you're not a Julia fan, I am, so I recommend the language to you. Yeah. Okay. Now I want to go to something that hasn't appeared in the literature, but I think is interesting. So, least squares dates back to Gauss. And it's one of the most studied problems in all of computational mathematics. But I think there's something that's been missed here. Now, estimation of your unknown x reduces to solving the normal equations. That's when you have an overdetermined problem. If you have an underdetermined problem, you might put a penalty on the norm of x and solve that problem instead. But the way these problems are solved, you take this A transpose A, which is called the grand matrix. You take a matrix factorization, which is usually something like a QR decomposition or a Cholesky decomposition, and then you can solve the linear equations. Okay, and the computational complexity of this is, well, you have to form the grand matrix. That's if a problem dimensions are m and p, that's m p squared operations. If you take the Cholesky decomposition of the grand matrix, that's on the order of p cubed. So these, for very large systems, which we're encountering nowadays, the rate limiting step is often solving these least squares problems, dealing with the linear algebra. Now I want to show you how you can attack this and using GPUs. So we'll use Jensen's inequality. That's the inequality on the top line. Now what I've done there is the VKs are just vector points in some higher dimensional space, and I've added and subtracted off the sample average of those points. That's the V bar. And then I've decorated by the iteration number n. And this is Jensen's inequality at the top. This is the chord above the graph property. And that, in fact, is a majorization, because when the Vk equal to Vnk, you get the same left and right-hand sides. You get tangency. Okay, so how does that work in least squares? So you take the A matrix in the blocks, and you take the x, the unknowns, in the blocks, and when you multiply this matrix times that matrix, you get AX. So we haven't done anything new. We've just represented the least squares in a different fashion. But now we can apply to the extreme right our Jensen's inequality trick. And when we do that, we separate the parameters. And the parameters are separated along these blocks, U1 through UK. And you can actually solve each of the pieces. So when you separate the parameters, you work piecemeal, updating one block at a time. Actually, you can do them all in parallel. And these are the updates. And they involve these Gram matrix inverses But the nice thing about that is these AK matrices are much smaller. So a lot of the burden of doing the matrix numerical algebra is lessened. Remember, computing a Cholesky decomposition is p cubed. If you have 10 processors, what's going to happen? Each processor is going to get a problem that's much, much smaller. Okay, so at each step you compute these residuals. This is a single matrix vector multiplication. You can compute and store these guys on the GPUs. And this is now your computational complexity. M is the, let's see, number of observations. K is the number of blocks. So that's going to go down a lot. So if K is 10, this is 1 over, has a 1 over K squared of 1 over 100. If K is 50, that's 1 over 2500 reduction. So that's a big deal. Now here I've shown the speed up. So the higher the bars, the better. A horizontal axis is the number of blocks. Purple is Julia's built-in way of solving least squares problem. This is parallel MM, what I've just described, using CPUs. This is with GPUs. So the CPUs don't give us that much because we're increasing the number of iterations. We have to iterate it now. So there's a trade-off between the complexity of each iteration and the number of iterations. But you can see with the GPUs, there is a substantial increase in the speed when you go to the parallel version. And this is the underdetermined case with regularization, even better here. Now the GPU version can be hundreds of times faster than the standard version. So something you can do with least squares. How's my time doing? 5 minutes? Okay. I'll probably have to skip a lot of things. 10 minutes? Okay. So this is a robust regression. So you notice the top equation, the residual squared occurs in the denominator as well as the numerator. So as the residual becomes large, instead of the contribution to the objective growing quadratically, it's cut off. The upper bound of this, one of those terms is actually 1 if C, when the residuals squared go to infinity. Now, we're going to look at this problem. Here is h. We want to study this function h of s. And you can imagine we're going to replace s by the residual squared. Here's the derivative. And I believe this function as second derivative. Okay, so this is a concave function. So one has to verify that through the second derivative. It's clear you're going to get a minus sign here. But then you have this hyperplane inequality. And when you apply that, you get a surrogate. You're going to substitute for the s, the residual squared. This derivative here propagates into the weight. That depends only on the current parameter value. So your surrogate function is a weighted sum of squares. And you can solve weighted sum of squares by pretty much the same technology as you solve ordinary least squares. So there's the majorization. That's the function at s n equals 1. So you can do robust linear regression very easily by transforming it into iteratively re-weighted least squares. Someone defined the applied mathematics is the art of turning unsolvable problems into solvable problems. Here the solvable problems are least squares problems. Okay, this last example is a genetic example. So I got interested in this by the problem of trying to put, say, criminals or some unknown person on a regular geographic landscape. So you can imagine taking something like China or Europe and pixelating that area. And to each area, you may or may not sample a certain number of individuals. And you type those individuals. Now we're just going to consider a single genetic locus with 2 alleles. Okay? Now some of those pixels may be out in the desert. There's no one you pick up. So we want to estimate the allele frequencies, say of the reference allele, across the landscape. And we do it by maximum likelihood, but we add in the addition of smoothing. So smoothing allows you to generate what's called a cline across the landscape. And basically, your allele frequency for a given pixel should be close to the allele frequency of a neighboring pixel. Okay. So what are neighboring pixels? So if they're little squares, you have 4 pixels, because you have 4 sides to a square, 4 neighboring pixels. If you introduce the pixels that just touch at the edges, you get a total of 12. Let's see, 8 neighboring pixels, but they have different weights. 1 for nearest neighbors and 1 over the square root of 2 for diagonally nearest neighbors. Okay, so what we do is we take the likelihood and we penalize it by something that introduces smoothing. So what it's saying is, if I and j are neighboring pixels, using the weight for those neighboring pixels, we introduce a penalty which depends on the difference squared of the allele frequency assigned to the pixels. So in pixel I, we observe CI reference alleles. We observe DI over 2 reference people. That means DI alleles in total. This piece is the binomial. So this is penalized maximum likelihood. And this tuning constant mu determines how much we smooth. If we set it too high, all the pixels have the same value. If we set it too low, there's no smoothness. Okay. So if you just look at the loss, or the log likelihood, the parameters are separated. You can optimize on any PI separately from any other PI. But this ties the pixels together. So problem is not parameter separated. So what you do is you take that term, that squared difference, and you majorize it, and this is a use of Jensen's inequality. So you take the average of the current neighboring estimates, you add and subtract that average, and then you use the convexity of the x squared function. And when you get done, you get this right-hand side of the inequality at the top. Now, the parameters are separated. And if you differentiate with respect to pi, you get an equation that depends only on pi. It can depend on the other p's, but only through their current known values. So you need to solve this equation. What you do is you multiply through by the right factor. You reduce to a cubic polynomial, and you can find a root of that, and there will be a single root between 0 and 1 for the allele frequency. So in this way, you get a smooth estimate of allele frequencies across the whole landscape, pixel by pixel, and you're pushing information from highly sampled pixels into pixels with low information or no information. And if you do this at enough independent SNPs, then you will get information that will allow you to take a random sample and say, oh, where does this individual originate on the landscape? We can place them by using Bayes' rule, using all the information across all these SNPs and the estimates from the pixelated and smooth Kleins. Okay, I've probably run out of time. Happy to take questions.